Hi, I'm Dr. Frank Ridgich, Professor of Computer Science at Dalhousie University and Canada CFAR Chair in AI at the Vector Institute. I've put together this series of videos and associated Python practices for anyone getting ready to study machine learning or AI. So you may be a student entering a course on these subjects. You may be returning to these subjects after some time away. You might be interested in learning AI for work. Or maybe you're just curious and want the foundations of AI and machine learning to feel less mysterious than they may feel. So I'm providing this for a few reasons. First, I'd like to help you and make your journey through machine learning and AI start on firm footing. And hopefully this will help better prepare you for your journey ahead. Second, I want to emphasize that machine learning is not magic. Machine learning and AI is built from mathematics and various associated tools. So we want to know data, we want to understand functions, probabilities, optimization, algebra with vectors, how to do scientific experiments effectively, and how to communicate clearly. When any of those components and a few others are shaky, then AI can feel like a black box that we don't understand, which is a position that we neither should nor be in. So this series of videos and this practice is not magic. It's not a silver bullet or some kind of cognitive pill that will automatically make you great at AI. It's more like a map or a refresher to hopefully widen your perspective a bit, give you some confidence, and help you understand what you need to know to move forward. We'll see several concepts that matter. We'll try them in Python, and we'll build the habits of thinking carefully. I want to emphasize that AI is computer science, so we're going to try to be treating these subjects as scientists. So we're going to go through these 5 arcades, and then there's going to be a little epilogue. Initially, I was going to set everything up as like a video arcade, and you're going to go through different booths and try to overcome challenges in that sort of game-like way, but I decided to take it back into the classic meaning of arcade, which is kind of visualized here, which is still a series of installations that we're meant to pass through. And this seemed a little bit more up to the task we have ahead of ourselves. It's not a game, even though it can be fun at various stages. So Arcade 1 will focus on linear algebra, that is to say vectors, matrices, dot products. Arcade 2 will be some calculus, mostly derivatives, and how things change locally. Arcade 3 is probability and base rates, distribution, statistics. Arcade 4 will focus a little bit on the programming language Python. One of its inherent library is NumPy, and techniques called vectorization. Arcade 5 will talk a little bit about plotting and evidence, mostly within the context of communication. When we do experiments, we need to make sure that we're telling the truth to others and to ourselves. And then finally, we'll wrap up with sort of an epilogue, which is sort of a gate or a door we want to pass through, beyond which is our eventual studies in machine learning and AI. So this is, I'm calling a Readiness Arcade. We're just trying to prepare to learn AI and machine learning, but it's not a course in machine learning. It may feel like that at some points. It might even feel occasionally that we are doing some instruction, but it's not that either. We're going to try not to go into too much depth. Rather, we're trying to just provide a bit of a map on the topics I mentioned so that you can be more ready when you get into the deeper studies. What that means, for example, is that there are some topics that we won't necessarily see here, but you'll see elsewhere. So this might be fitting regression by gradient descent. This could be, how to tune learning rates and other what we call hyperparameters to make learning easier. It could mean stochastic gradient descent and mini-batch SGD. Logistic loss gradients, backpropagation, and neural network training generally. We're not going to see those topics here, but we're not meant to. So again, these slides here are kind of a map of the topics, and we're going to go through them relatively quickly. And then the notebook, the Jupyter notebook, the source code that I'm also providing, is sort of like a gym in which you're going to practice these topics that we'll be talking about in these videos. So again, here's just a definition of what the arcade is in a classic sense. And for each of these stations, each of these arcades, we want to sort of look at the math that I'll show you and try to predict what you expect from the math before you run the code that implements that math. So source code and mathematics are oftentimes very closely interrelated to each other, and like abstract mathematical concepts can be implemented in source code. So we'll be running some of the mathematical concepts we're talking about, and can you predict the math before you run the code? Can you do the computation in your head, basically? Once you do that, you can go into the notebook, the Jupyter notebook, complete the notebook cells, fill in some source code, and try to run it. You'll run into failures. Everyone will run into failures at some point. It could be a missing character. It could be something more severe than that, something more serious. And you're going to try to repair those failures yourself. This isn't a course, so there's no teaching assistant looking over your shoulder who can help you find those failures and recover from them. You're going to have to do it yourself, but that's part of the learning process and the preparation process. This is something that a lot of people don't actually do, but it might actually be instructive or helpful for you here. When you run into failures, or even when you don't, but you kind of have to think your way through these first 4 steps, it can be helpful to write at least one sentence explaining, what changed in your thinking, what you had to realize in order to solve these components of these arcades. So again, mistakes are going to happen. Mistakes don't mean that your skills are insufficient to learn AI or machine learning. It doesn't mean that you're not going to be successful in the future. Rather, it's good practice just to notice and investigate them. It's like mindfulness. You're going to notice these things occurring. Even noticing them in the first place, these errors, is part of the journey. It's helpful to you, gets you stronger. And then obviously overcoming them and investigating them will be part of that journey as well. So before Arcade 1 begins in the next video, if you could open up the notebook and complete the start screen diagnostic. So this is just a bit of sections that you're meant to complete to see where you're starting from, basically, on your journey. Imagine like a board game map with the start at the beginning. That's where you are right now. So you're not going to be graded, but basically we want to understand, you want to understand where you're starting from in terms of linear algebra, shapes and matrix multiplications, standardization and leakage, which again, these are topics that might actually occur in machine learning, but I'm going to just evaluate them initially. Derivatives and gradients, that's a series of topics that a lot of people getting into machine learning might be a bit rusty on, so just practice those. Probabilities, base rates, statistics, hugely important in machine learning, so make sure you're starting from some place of understanding there. And then, validation, baselines, and kind of scientific evidence. What's your perspective on those currently? You're going to get a score, and the score will help you identify what needs focus. So if you get a score of between 0 and 3, you should watch all of the videos in this series very carefully, go back, watch them again, and do every notebook check in the associated Jupyter notebooks. If you get between 4 and 7 in the score, watch all the videos again, but maybe just spend your time or spend most of your time repairing the checks that you kind of fail on or don't pass. If you're already getting an 8 to 10 score in this initial diagnostic cell, then you can move a bit faster. You might still want to watch all of the videos, but the main component will probably be that final gate, that final door into machine learning, that final boss. These are all synonyms of the same section of the series. And this will be your kind of main readiness test to move on to learn machine learning. So just a bit of background before we jump in, like what are we kind of preparing for anyway? What is the goal or the light at the end of this little tunnel? So a traditional program written over a decade ago might have been something that a human or a team of humans wrote down, possibly collaboratively, to solve some kind of problem. And that problem might involve making decisions in the real world, like is this email spam or is it not spam? So a traditional program has humans write these rules, if it has words of this type or capitalization of this type, or if it comes from this kind of email address, or if it's addressed to these kinds of recipients, all written down in a massive big chunk of code. That's how we would do things traditionally before machine learning. Machine learning learns patterns that can behave like rules from lots and lots of examples. So humans, or a team of humans, collected many, many emails, labeled them. These ones are spam, these ones are not spam, and then fed these into an algorithm that learned the difference between them. So a traditional program, we just follow the rules that humans wrote, but now the model that has learned the program or this pattern will be presented with a new email that it's never seen before, and then try to classify this email as either spam or not. So in the old days, traditional programs were fairly effective. People were writing code in computer science for many decades, and it was fairly straightforward and useful and successful when the rules of these patterns were relatively clear and well understood. But even spam, sometimes it's hard to identify, especially these days, an email, whether it's spam or not, given its context. Sometimes they're very well written, even if they're not written by a human. And they might even have certain elements of it that appeal to an individual, the recipient, specifically. And so this can be problematic if you're trying to identify whether this is spam or not. A traditional program will have its output computed directly, so we just compute the output and then it's sent along on its merry way. In machine learning, the output is predicted. Maybe there's a score associated with it. Maybe there's a ranking of this collection of emails, the probability of these emails being spam or not. And then that is passed on to some other downstream code. So here's a little example. So imagine we want to investigate this machine at this gate in our arcade that we're about to enter into. So if the bronze casing is hot and the pressure needle trembles a certain amount with a certain frequency, this could be a hard-coded rule that we use to mark this gate as unsafe. So if these conditions are met, then this is the label. And it's deterministic. There's no room for wiggle room or statistics or randomness. It's if this, then that. Now, in machine learning, we don't necessarily have something as clear-cut as this rule-based decision. Instead, we would have many, many examples. Here, the example is 2,112 examples, for some reason, of records from this gate machine or gate machines like it. And in all of these over 2,000 examples, we have recordings of temperature, pressure, vibration, the age, maybe the time of day, maybe the weather, and so on and so on and so on. Lots of information are recorded. And we also have the recording of whether the gate failed around that time of the recording or not. So we don't have any rules yet. We just have lots of examples of failures and non-failures. We're going to pass these 2112 examples to the machine learning algorithm, which will then kind of tease them apart and identify which of all of these records, these measurements, are actually useful to the decision, which are not. And it'll learn how to make the decision of, given a new set of measurements, whether or not the gate should be labeled as unsafe or not. And that decision will be somewhat probabilistic or stochastic. It won't be as clear-cut as the rule-based example. It'll have some uncertainty to it, right? Speaking loosely, a machine learning algorithm could still label a set of measurements as indicating the door is safe or unsafe, but it'll say, well, I think it's 70% unsafe and 30% safe, or vice versa, or anything in between. So this archive, this collection of data that we have, is hugely important to be able to tease apart what constitutes an unsafe pattern from a safe one. But this introduces some benefits over the rule-based system and some drawbacks. So benefits are that we're less likely to encounter bugs or errors in the coding generation process. So humans are subject to error, and if this rule that we wrote over here is too simple for real gate machines, then it'll fail in a whole variety of different ways. Right? It's not really up to the task, the complexity of the task. Maybe the safety of the door is really a much more complicated scenario than this rule-based system might indicate. So having a lot of data and really taking a ton of measurements and really understanding or measuring aspects that can help us understand the nature of this doorway, this gate, ought to give us a more fine-grained, detailed picture of the mechanism we're trying to study. It's a little bit more scientific, empirical anyway, data-driven. But it also comes at a cost. So imagine that the archive, this collection of data, which we sometimes call a data set or a corpus, it's language data. Imagine if we have tons of measurements from calm summer days, and we've recorded all this data from well-maintained gates that are relatively new. Okay, so a bit of a checkpoint here. I'm not going to answer this question for you. This is a question for you to try to think about right now. What can go wrong in that scenario when we would use a model trained on data from that kind of archive on a gate that is weathered, it's outside of our promenade or our arcade, it's wintertime, maybe it's less well maintained, and so on. So what can go wrong if we've trained a model to differentiate between safe and unsafe gates in this first scenario, if we have data that might not match it when we try to use it in practice? So many what we call supervised machine learning problems can usually be described with one table, if we're lucky. The table can look like this. Here's another scenario of trying to look at data from students in a course and trying to predict whether or not they're going to pass that course. So we have students, their names are A, B, and C, and we have a little bit of measurements on them as well. We have somehow the hours that they've studied. So student A has studied 3 hours, for example. Somehow, we also have the number of hours that they've slept. So somehow we know that student B has slept 8 hours, maybe on average. And then in our course, we had a bit of a practice exam at the beginning of this course, graded on 100, and we have their scores from those practice exams. And we have, for example, student C has obtained 72% on that practice exam. And then time passes, and eventually these students complete this course. And then at the end, we have labels that we automatically can assign to each of these students. The binary label, yes or no, and it indicates whether they passed or not. So in this case, unfortunately, student A did not pass, but students B and C did pass. So this is what we call a supervised machine learning problem. We have some data or measurements that we use in order to make our predictions. This is hours studied, sleep, practice score. And then we also have another variable, which is the variable we're trying to predict, whether they pass or not. So in practice, you can expect some other student Z, for example. We somehow have the measurements of how many hours they've studied, how much sleep they get, and what their practice score is. We don't know if they passed or not, but given all of these other examples of all these other students, and a machine learning algorithm that can use those measurements to predict whether they passed or not, we can make a reasonable prediction about whether the student is going to pass or not. This is a toy example, but I think it gets the message across. So we have a table like this with many, many rows, many of them not shown here. These are examples, we call them cases, observations, data points, etc. The columns of this table are mostly what we call features, variables, or measurements. I called those things a moment ago. We can separate out the columns a little bit. So all of the rows from top to bottom, where we're looking at just the measurements, hours studied, sleep, and practice score in this example, we can usually call that X. That's a big X because it's a big matrix, so we call it big X. And then we can kind of cut off the last column. That's a vector of essentially binary numbers. No's or yeses or zeros and ones. And because this is a vector, we use a lowercase letter, and we call this last column by itself just the letter Y. A model will map big X to predictions Y. And then eventually we'll get new data we've never seen before, give those data to the model we've learned, and that will make new predictions Y hat. I'm not sure if you can see it here, we'll see it a bit later, but that kind of circonflexe, the little diacritic or accent we have on top of the Y, that's Y hat is what we call it. So that's a prediction that may or may not be correct. And indeed, the error will be the difference between the prediction that the model makes and the actual target we know to be true or not. And the difference, this error, can be measured by a metric or a loss, depending on what we're using it for. The difference between a metric and a loss is not so important right now, but we ought to come back to it a bit later. So imagine we can record much more data than we have in this table. Consider what column would you never include in your input variables big X if it was created after the final grade was known. So imagine we have many, many more measurements, many, many more columns in matrix big X, which here only has 3 columns, but we add other things like their diet and the prerequisites that the students have taken, and maybe scores on previous courses, et cetera, et cetera. But imagine we can also record information after the final grade was known. So they took their final exam, and we have all the information from their assignments, and we have information from a course they registered in next semester. So just speaking very loosely and thinking very broadly, what kinds of information would you not want to include in big X if you're trying to predict whether the student passed or not? There's no wrong answer here. I just want you to think about that question for a bit. We will come back to it in later videos. So how do we make decisions in a noisy world? This is very important to the machine learning process, the machine learning topics, but it's also something that can help us in our day-to-day reasoning. We want to be able to organize our thoughts systematically. Okay, so the pipeline we tend to imagine in machine learning is one that might apply to our daily lives as well. There's a world that's very noisy and it's somewhat hard to understand, but we can take measurements from it. We can acquire data from the world, and then we can organize that data into patterns, and that those patterns reveal information about the world. You know, how these variables in the recorded data go up and down together, how they change together, how they don't change together. This is all information that we're kind of shifting out of the data. That information then can be filtered into what we'd call evidence, evidence of a scientific claim or evidence of a theoretical understanding of the world, which we're gradually bringing into focus. And that evidence can take the form of claims about the world, comparisons about 2 things in the world. It can even be in terms of the measurement of the uncertainty we have in the world, which might be diminishing. Once we're able to make claims and comparisons about the world through evidence, and we're able to quantify our confidence in that evidence, then we might want to take some action in the world. We might want to take a decision that somebody can inspect. So here are some examples. I want to emphasize that a single number by itself is rarely evidence. This is really a comment that might be more applicable for a course in machine learning, but it always bears repeating, which is occasionally you'll see research papers, or you'll hear people talk about machine learning models, and they'll use 1 or 2 numbers, a handful of numbers, to basically emphasize how strong, powerful, or useful the model is. And those numbers will tend to be, maybe 1 or 2 numbers, broadly something like accuracy, and that's really not sufficient to make a meaningful action in the world. It's not enough. So here's a couple of examples. Imagine if you're running a website, and you're telling somebody, like you have a company that has a website, and you say to someone, hey, we got 10,000 clicks last month. 10,000 might sound like a big number to some. It might sound like a small number to others. It doesn't mean very much without more context. What is a little bit more useful is information. So, again, distilling down actual knowledge from the data could be something like, well, the click rate rose from 3% last month to 4% this month. So the click rate has increased somewhat significantly. And then this kind of somewhat more detailed quantification allows us to pull out evidence. So the new user interface we designed for our corporate website, for our app, whatever it might be, beat our baseline on some held out users that we did not use in the development of this new UI. Okay, now we have some evidence. Not only did the click rate rise, but it rose, and it rose specifically because of our changes we made to the UI. That's evidence that we are after in the first place. In machine learning, a lot of claims are replete with just, well, the model accuracy is 94%, and 94% sounds impressive. It might be an A grade where you come from, but it might not be enough on its own. Maybe another model that is far simpler or cheaper is 97% accuracy, for example. So a better claim might be that our model beats the 90% majority baseline. So it's a 94%, and the best other alternative that we could come up with was only 90%. So we've increased 4% over that baseline. Not only that, but also we can claim that we improved recall for the rare class without leakage. So maybe we're trying to make predictions in a hospital, and there's some rare diseases that the old model is just very bad at finding, but our new model that gets 94% on average also identifies these rare cases. And it can do so without kind of cheating, without taking information from measurements that it should not have. And finally, imagine we're looking at a course and we say someone's average score is 78. Well, is that student doing well? Are they doing poorly? Are they getting better? Are they doing worse over time? So better information, again, has some kind of comparison. We're comparing and contrasting. We can say, well, the average score is 78, and the scores have actually risen after some tutoring. And not only that, but the comparison uses a fair reference group. There's an uncertainty check, and we were doing other things not shown in the slide that demonstrates that this score of 78 is a significant improvement for this student. So again, another checkpoint for you to think about. There's no answer here I'm going to give you, but I want you to think about it. And I want you to kind of be mindful of whether or not the question even makes sense to you. Is what is stronger evidence? Saying the model got 98% accuracy, or the model beat a baseline on held out data without leakage? Maybe the answer here is obvious to you, but I want you to think why, right? I kind of went over it relatively quickly, but this is the kind of baseline we want to be able to have if we're going to eventually go into machine learning. Why might the latter of these claims be stronger in terms of evidence than the former? So think about that for a bit. So all of these tools can help organize our thoughts. Linear algebra, which can help us hold and manipulate our data. Calculus can help us organize our thoughts. It describes local change, and in machine learning especially, it describes small changes over time. And this is essentially a major engine in machine learning. And we'll see a little bit of why that is in this series. Probability and statistics is hugely important in machine learning and scientific experimentation generally. And I find that having a firm footing on probabilistic thinking and statistical thinking can actually have a lot of benefits for you in the real world, in your day-to-day lives as well. So it really helps to get deep into probability and statistics. NumPy might not help you in your day-to-day activities, but it is important in machine learning, and it does a lot of the computational work for you. And then finally, if we have acquired this evidence after this process of going from data to being able to make justifiable claims, how do we communicate that evidence to others and to ourselves? Okay, so we need to interpret our claims. If we're going to take actions that can actually affect people or affect ourselves, we better make sure that the communication is as clear as possible. So all of these 5 points you can consider as tools in your tool belt that will help you not only help you think more clearly, but actually do the work of machine learning and artificial intelligence much more effectively and much more successfully. So throughout the arcade, you can imagine going through doors. The first door is just the concept itself. What does this symbol mean? What does this picture mean? What does this idea mean? And hopefully you'll be able to answer that somewhat abstractly as you pass through these arcades. Door 2 is some actual work, so some calculation. Try to do the work yourself. Try to predict what the machine will produce for you. Do it on paper if you have to. Do it in your head if you can. But then you're going to take that mathematics and pass it through door 3, which is running it in Python, the programming language Python. You'll try to reproduce, test, visualize. You'll be writing lots of code, and you want to make sure that your understanding of the mathematics of the process and the code match up against each other. Sometimes you might have made a conceptual error and the code is correct, and you need to refactor your thinking. Occasionally, the code will have some bug in it, and you're just really certain, and you can verify that your thinking is correct, in which case the code needs some changing. Either of those things are going to happen to you, and through practice, you'll be able to identify when you've made a cognitive error and when the code is at fault. But every arcade will have you passing through multiples of these doors, 1, 2, 3, 1, 2, 3, 1, 2, 3. So again, AI and computer science more broadly is a science, and like any scientific discipline, we're not studying magic. We're not just pulling incantations off of shelves and reciting magical spells. Machine learning, despite its great complexity, is understandable, it's predictable, and we can make falsifiable claims about it. It's not just an API call to these large companies. You can do it yourself. I wanted to provide links to some other free resources to you. So there's mostly YouTube videos, some websites that describe visual intuition, linear algebra, calculus, probability and statistics, Python, and evaluation. So click through these links at your leisure and learn more about them. I'll also highly recommend a course I taught recently in data science. This is a first-year computer science course, but because it's first year, it'll hopefully be accessible even to people not necessarily studying computer science. I recommend this in particular because I like it, but also because it goes into much more depth on the important topics, which we'll only be touching on in this kind of Readiness Arcade. I hope you don't get stuck in the intuition phase. Don't just try to have a complete, total understanding of a concept before you move on. Really, a lot of the learning in an empirical science comes from the doing of it. So get your hands dirty with the code and don't be worried about making mistakes. A lot of your intuition actually will just come through practice. It's not something you can just will into existence through careful logical thought. So do the exercises, do the coding. Don't worry about being fast either. Don't try to rush through everything. If you kind of complete everything without getting confused occasionally, without making mistakes, then you've wasted your time. Before you actually do the relatively hard work of learning machine learning, you ought to be able to say sentences like these truthfully, that you can manipulate matrices, weights, shapes, and predictions, both theoretically on paper and in code. You'll be able to say, I know how a derivative is local change, and you'll be able to go a bit deeper than that ideally. You'll be able to say, I know why the probability of A given B is not the same thing as the probability of B given A. If this notation is unfamiliar to you, it'll become familiar in our arcade coming up. You'll be able to say, I know why one score or one measurement or one plot is not automatically evidence of some claim and why that is. You'll be able to say, I know why making predictions doesn't necessarily tell you there's a causative relationship between the thing you're predicting and all of the information you have about that thing in the first place. And also remember, even though we are going to go into what might occasionally feel like instructive depth in this lecture series, it's not really a course. It's not a replacement for your course prerequisites. If you happen to do well in one of the arcades that happens to correspond to a prerequisite course that you need to take a machine learning class, this is not a replacement for any of those. You're going to need to have validated university prerequisites for university courses, obviously. There's a saying I like, ancora imparo, which basically means I am always learning. It's always something nice to have in the back of your mind. Always be curious, always try to be open to new information. And with that, let's dive into the first arcade.